Hey guys, welcome back. We'll continue with the book Cracking Codes with Python, and in this video we are going to hack the Vigenère Cipher using two different methods. Let's get right into it. There are two different ways to hack the Vigenère Cipher. The first method is to use a brute force dictionary attack, where we try out every word in a dictionary file as the Vigenère key, but this only works if we're using an English word key. The second method, that's more sophisticated, was used by the mathematician Charles Babbage, who first broke the Vigenère Cipher, and it works even if the Vigenère Cipher was encrypted with a key that consists of random letters, so not English words. In this episode we are going to write programs that use both different methods to break the Vigenère Cipher. Now for the first approach, using the dictionary attack, we actually need to download the dictionary file that includes 45,000 different English words, and we're going to use that to compare the keys against that to see if that breaks our encrypted message. And for that we can head over to the resource page for the book, link in the description down below. And if we scroll to the very bottom of the page, we can then download the source files for the book. And in there we're going to find the dictionary.py file, which we need to move to the same location where we're going to place our program that we're writing to break the Vigenère Cipher. So to get started, we can open up idle and then create a new file. And we can save the file as vigenaire-dictionaryhacker.py. And again, in the same directory where we are saving this Python file, we also need to make sure that we add the dictionary file that is included as part of the book's resources. Now, and we are going to start our program with importing three different modules. The detect English module that we wrote a couple of episodes ago, then the Vigenère Cipher module, which we also wrote previously, and of course a paperclip module in order to copy and paste the decrypted message later on. Inside of our main function we have our ciphertext that we want to break, and then we have a function hack Vigenère dictionary, which accepts the ciphertext as an argument, and the return value of that function is going to be saved in hacked message. Now the hacked message is either going to contain a properly decrypted ciphertext, so the plain text, or it's going to return a value of none. And we're checking for that next. So if the hacked message is not equal to none, so if we actually have a plain text that was decrypted, then we're going to print out that we're actually copying the hacked message to the clipboard. We are then printing out the hacked message, and we are copying that message using the paperclip module. If instead the hacked message variable is set to none, meaning we were not able to hack the ciphertext, then we're going to print out a message indicating that the decryption process, the hacking process, didn't work properly. And then of course the logic itself takes place inside of our hack Vigenère dictionary function. That function accepts the ciphertext as an argument. And then we are going to use the open function in order to open our dictionary file. We're going to store that in FO, and then we're going to read all the individual lines. And of course each English word is in its own line, and that is going to be saved inside of words. Once we've done that, we can then close the file. Now next up, we're going to loop over the different entries in our dictionary, and we're basically going to use each individual word as a key, trying out if any of those English words has been used as a key to decrypt the message. Again, that's only going to work as long as we are using an English word as an actual key. If it was a random number of letters that has been used as a Vigenère key, then we won't get a valid result. But by looping through each of the different words, we are first going to call strip on the word to remove the new line at the end, so we actually just have the word. And then we are going to use our Vigenère Cipher module that we imported, and we are calling the decrypt message function that is defined inside of that module, and we are passing that individual word as well as the ciphertext to it. And that function of course is going to decrypt the message using that specific word as a key and the ciphertext as a message. And the message decrypted by that specific key is then stored in decrypted text. Of course that might be total gibberish if it's a wrong key, so therefore we next need to figure out if it's actual proper English. For that we are going to use our detect English module, and we're calling the isEnglish function, passing the decrypted text that we just got, as well as the parameter of the word percentage, so we set that to 40%, as arguments to the function. And now if our isEnglish function actually returns true, so that our function determines that there's a high likelihood this is actual proper English, then we're going to execute the next steps. Otherwise, we are just going to continue with our loop trying out the next word. So we are only taking a look at the decrypted text that return a message that looks like proper English. So here we're printing out that we have the possible encryption breaks here. We print out the key, which is of course an English word. And then we are going to print out the first 100 characters of our decrypted text. We can then have a look if that's actual proper English. And if it is, we can press D on our keyboard, or we can just press enter if it's not proper English, and then we're going to continue trying out the different words. And if at any point we pressed D to confirm that it's proper English, then we're going to return that decrypted text. Otherwise, by default, we are going to return none. And then of course, we're going to get back the message that it was not possible to decrypt the text using the English dictionary words. So let's actually run the program and let's try to decrypt that ciphertext here by trying out all the different English words. So as long as the key is actually an English word, we should get a proper value. So as we run that, we can see there is our first possible option here, the key astrology. But if we take a look at the text, we can see this is a proper English word, but this doesn't really look like proper English. So actually that is not valid. Let's just press enter. And we have another possible encryption key that returns a message that looks like proper English. If we take the key astronomy, then we get back the real secrets are not the ones I tell. That is proper English, so let's press D to confirm this. And now we can see this is our decrypted message, so the key astronomy was indeed the key being used. And our message here is proper English, and it's also copied to the clipboard, so we could paste it into any other application. So using this program here and using a dictionary attack, we were able to decrypt the message. But of course that only works as long as the key being used to encrypt the message is actually an English word. And we learned before that that is not very secure, precisely because of this reason here, because someone could just try out all the different English words in a dictionary. If the person encrypting a message is actually aware of that and uses a random sequence of letters as a key, then this approach won't work. And in that case, we need to use a different approach. And of course, we have a number of different challenges in this case. We covered in the last episode that we can use frequency analysis to actually break a ciphertext even if no English words are being used, but we need to figure out the length of the key in order to do so. And there's a method to do that, which was actually identified by Charles Babbage originally, and then later on formalized by the mathematician Kaczynski, and this approach is actually named after him. And in order to identify the key that has been used, what we basically do is we look at the ciphertext and we are looking for any kind of letter sequences which are repeating. So here's an example. We have the plain text, the cat is out of the bag, and it was encrypted using the key spill the beans. And if we take a look at the plain text and we compare it to the generated ciphertext, we can see that in both cases we have a certain sequence of characters that repeat. So for example, here we have the word the, which is repeated at the very beginning and then later on. And of course, as we encrypt that plain text into ciphertext, we have of course different letters, but the same letters are repeating. And that's the case because in this case, incidentally, we are repeating our key spill the beans just as the point where we have the word the repeating again, and therefore we get back the same sequence. That's of course a very convenient coincidence for us. We are going to cover also how we can deal with the situation if that's not the case. But in this case, the key is repeating at just this point, and therefore we can basically have a look at that and can simply count the number of characters between the repetition of the same sequence. In this case, this is a value of 13, so there are 13 characters until the same characters repeat again. And therefore there's a good chance that because of the spacing, 13 characters, our key would actually be 13 letters long. Now that's of course a hypothetical example where we have the special case that our key repeats at just the point where the same word is used again. Let's have a look at another example. So here we have a longer ciphertext, and if we just remove all the white case characters and we just have a look at the actual letters, we can add them to a single string, as we see down here, and then we can have a look at the sequence of the different characters and see which kind of characters are repeating. So here we can see that YBN repeat. There are actually 8 letters in between, so we have an 8 letter spacing. And then we have other characters that repeat, for example VRA repeats also 8 letters in between. Then after 24 letters, VRA repeats again. After 32 letters we have a repetition, and also after 48 letters. So by looking at that, we can see there are several potential key lengths, ranging all the way from 8 to 48 letters of repetition. And for a better example why our key could be 8 letters long, but also for example 24 letters long, let's have a look at an example. So here you have a plain text message, the dog and the cat, and it's being encrypted by 2 different keys. The first key is ABCDEFGHY, and the second key is XYZ. So if we encrypt our plain text message using that specific key here, we can then have a look at the ciphertext and figure out when the different letters are repeating. So here we have the sequence TIG, which is repeating, and if we count the number of letters after which that's repeating, we can see that we have a spacing of 9, and that's actually the number of letters that we also have in this key here. So in this case, actually, the sequence of repetition is able to identify how long our key is. But if we take a look at another example, in this case we encrypt a plain text message using the key XYZ, we can see we get this ciphertext back. And here again we have those 3 letters which are repeating. And if we count this here, then again we get a value of 9. So we could assume that our key is again 9 letters long. But in this case that would be wrong, because our key is actually only 3 letters long. So in fact our key could be as long as a number of letters until we repeat a certain sequence of characters, or it could be a factor of that. So in this case 3 is a factor of 9, and therefore our key could, in this case also is, 3 letters long. So in our example here, we could have a look at the different possible key lengths, so 8, 24, 32, 48, and figure out the factors that they have in common. If we do that, we can see that the number 8 would have the factors 2, 4 and 8. 24 has of course additional factors, and we could have a list of all of those. And then we can see that the common factors are being used. We have the number 2 4 times, the number 4 4 times as well, and then for example the number 8 4 times as well. And the actual key length is most likely the most frequently occurring factor, and by just counting we figured out that 2, 4 and 8 actually occur most often, and therefore they are the most likely lengths of the Vigenère key. So now that we determined the possible lengths of the Vigenère key, we can now basically decrypt the message one subkey at a time. So to get started, we could, for example, try a key with a length of 4, and if that's not working, then we could try the other options, so 2 and 8, the ones that are most likely to be the key lengths, to decrypt the message. For that we again have a look at our ciphertext, and we identify every 4th letter, starting with the first one. And then we would repeat the same process, starting with the second letter, and again highlighting every 4th letter. And we do the same with the 3rd and 4th letter. And we would repeat that until we reach the length of the subkey that we are testing. Now if we do that, we are going to get this sequence here. So for the first letter, every 4th character would be this string. For the second letter, it would be this one, and so on and so forth. And since we are currently testing a key with a length of 4, we have those 4 different substrings. And assuming that we guessed the correct key length, in our case 4, each of the 4 different strings we created would have been encrypted with one subkey. And that means that when a string is decrypted with the correct subkey, and then we use frequency analysis, the decrypted message should be actual English. So let's open up idle and let's actually have a look at an example. We are starting out by importing our frequency analysis and Vigenère Cipher module. Next up, we're going to loop over all the different letters in the alphabet, and we are passing each letter as a potential key to the decrypt message function. And as a second argument, we pass the string that we just identified by taking every 4th character, which we can also see over here. So we started at the first character and then took every 4th character. And if 4 is actually the correct key length, then all of these characters should be encrypted by the very same subkey. And then we are going to print out the subkey used, our decrypted message, and we're using our frequency analysis module to call the English frequency match score function, which takes the decrypted message as an argument, and we get back a match score, and of course the higher the score is, the closer it is to actual English. So let's run this code here. And here we're trying out all the different letters from A through Z. We can see for the letter A, for instance, we get a score of 2, for B a score of 1, for D, for example, a score of 0, and we know the higher the score, the closer the decrypted words are to actual English. So in our case, the subkeys A with a value of 2, I also with a value of 2, as well as N, W, and X have the highest score and are therefore the most likely real subkeys. And then we would repeat the same process again for the 3 other substrings, which started at the 2nd, 3rd, and 4th position, and then also identify the most likely subkeys. And if we do that, we would get the following result we just saw for our example here. We had the following most likely subkeys A, I, N, W, and X. For the second one, we would have I and Z. For the third one, C. And for the fourth one, these different subkeys. Now, because of these different possible subkeys, we have 5 in the first case, 2 in the second case, 1 in the third case, and again 5 in the fourth case. We can multiply that by each other, so 5 times 2 times 1 times 5, and that's going to give us a value of 50. So this is the total number of combinations that we need to test for. So therefore we are going to brute force those 50 possible keys to see which ones most likely match to English and are therefore the correct subkeys. And so basically we are checking for those 50 different possible subkeys. So here, for example, we have the letter A from the first group, I from the second group, C from the third group, and K from the fourth group. That is a possible key. And we have 49 other combinations, and we are going to use that brute force approach to see if any of those 50 options actually return proper English, and then we know that is the proper key that was used to encrypt the message, which we can then use to decrypt our message. So now that we understand the basic principle and how our approach to hacking the Vigenère cipher is going to work, let's actually write a program in code in order to do that for us. So we're going to open up idle, and we're going to create a new file. And we're going to save that file as vigenarehacker.py. Now, and our program is going to first import a number of different modules. For example, the array module to work with regular expressions, but also our Vigenère Cipher module from before, paperclip, frequency analysis, and also the detect English module. We then specify a number of different constants, for example, for the different letters of the alphabet. Then the silent mode constant, which we can use in order to print out more output while our program is running. Then our number of most frequently used letters, which is a number of different letters per subkey. So in our example before, we set it to 4. And then we also set the maximum key length. So we are only going to try out keys with a maximum length of this. So 16 is going to be our upper bound here. And then of course we still need to identify any non-letters. And for that we are going to use our regular expressions module. And we're using it to exclude any letters from A to Z. So in our constant here we have our non-letter patterns. So anything other than letters can then be used to be excluded. We are then defining our main function here, which includes our ciphertext, and we are calling hackVigenère, passing the ciphertext as an argument to that function, and we are going to store that in our hacked message variable. And just as with the previous program, we are then checking if hacked message has an actual value. If it has a value none, then we know that we were unsuccessful in hacking that message, and we're going to print out failed to hack encryption. But if we got back a valid English decryption, then we're going to print out that we are able to do so. We're going to print out our encrypted message and of course also copy it using the paperclip module. Now, as we just covered theoretically outside of code, we know that the first step is to find any repeating sequence spacings. For that, of course, we need to use the message as an argument, and we are going to start out by removing any non-letters, which of course are not being encrypted in our ciphertext, from our message. So therefore we are going to use our non-letters pattern constant that we identified before, and we're going to replace those by an empty string, so removing them. And we're then going to compile a list of different spacing sequences found in the message, which we are going to store in a dictionary. We're then looping over sequences of letters between 3 and 6 and comparing them. So on the first loop iteration, we're always having a look at 3 different letters, and then basically looking if that pattern of 3 letters repeats. Then we're doing the same as 4, and so on and so forth. For that, we are going to determine what the specific sequence is, and then we are going to store it in a variable, and we are then looking for this particular subsequence, so for example 3 letters, in the rest of our message. If we are actually able to find a sequence that repeats, so for example 3 letters that occur twice in our ciphertext, then we are going to append the spacing distance between the 2 repetitions in that sequence, and then we are going to return that spacing sequence. And of course our sequence spacings here, that is a dictionary, and in our dictionary the respective keys are the sequences that we identified, and then the values are lists of different spacings. So for instance, we might have a key XBN, for instance, and maybe that sequence repeats after 8 characters and maybe also after 35. Then those 2 values, 8 and 35, would be added to a list as a value to that specific key. Now, as we covered before, we then need to figure out the different factors that the spacing sequence have in common. So in this case, if we have a number of less than 2, then we're going to return an empty list, because numbers less than 2 have no useful factors. And otherwise we're going to define an empty list factors, and then we're going to loop over the values of 2 up to the maximum key length plus 1. We are not testing 1 because that's not a useful factor, because if we had a key with a length of 1, that would basically be the Caesar cipher, which of course is not very well encrypted anyways, so therefore we're excluding it here. And then we're checking if the number we're looking at is equally divisible by 0, meaning that we identify a factor this way, and of course we're going to then append that to our factors list. And by the end, we're going to return a list of values, and we're using the set function to remove any duplicate factors inside of our list. We then of course need to identify the most common factors. For that we are taking the factor sequences as an argument to that function, and we are defining the dictionary factor counts, which of course is initially empty. And then we are using a for loop to loop through the different key value pairs inside of our sequence factor dictionary. And then we're basically counting each factor and increasing it if that specific factor occurs more than once. After that, we are going to put the factor and its count into a tuple and create a list of these tuples so we can sort them. For that we define an empty list, factors by count, and then we are looping over each factor, and first we are going to exclude any factors which are larger than the maximum key length. And if the factor is less than or equal than the maximum key length, which we initially set to 16, we are then going to append that factor to our factors by count list. After that we are using the sort function to sort the list by the greatest factor count, and we are going to return our sorted list. We then have an additional function called Kaczynski examination, which takes the ciphertext as an argument, and this function finds out the sequences of 3 to 5 letters that occur multiple times in the ciphertext. We also of course need to be able to identify the different subkey letters. For that we have the function get nth subkey letters, which takes the nth value, for example 1, 2 or 3 for instance, then the key length and also the message, and that returns every nth letter for each key length set of letters in the text. So for example, if we have a key of 4 that we are checking, we would first get the string for each 4th letter starting at the first character, then every 4th letter starting with the 2nd letter, then starting with the 3rd, and then starting with the 4th letter. And once we identified the most likely key length, we can use the function attempt hack with key length, which accepts the ciphertext and the most likely key length as an argument, and then determines the most likely letters for each letter in the key. And then finally we can put this all together in our hack Vigenère function, which accepts the ciphertext as an argument. And we first start out by doing the Kaczynski examination to figure out what the length of the ciphertext encryption key is. So here we are using the function Kaczynski examination that we saw before, and that returns all the different likely key lengths which we store in a variable. Then we're using a for loop to loop through the different key lengths in our variable or likely key lengths, printing that out so that we see what the different possible key lengths are. And next up we're then looping through all the different key lengths and trying to actually hack the message using this key length. For that we are using the function attempt hack with key length, passing the ciphertext and the specific key lengths to it, so trying out all the different key lengths that we identified. Now, and if any of those return a hacked message here, then we are going to break out of the loop. And if none of the key lengths we found using the Kaczynski examination actually worked, then we start brute forcing through the entire key length. For that we are checking if hacked message is equal to none, which is going to be the case if none of the key lengths actually work to break the message. And then we are looping over all the different key lengths, starting from 1 all the way up to the maximum key length plus 1. Of course, we don't need to check the key lengths that we already identified from the Kaczynski examination. So therefore we are going to check if the key length is not in the variable all likely key lengths, because we already checked that before. And then we're trying out the other key lengths by using the function attempt hack with key lengths with the ciphertext and the key lengths. And the reason we're putting the keys which are most likely based on the Kaczynski examination first is of course that we could break the message earlier than testing out all the different key lengths. And by the end, if we are able to identify a hacked message, we're going to return this. Otherwise, a value of none will be returned, and then of course the message will be printed that we were unable to hack the message. And of course you can find the program in whole also in the chapter which is linked in the description down below. Now that we went through the entire very extensive program, we can actually try to break our ciphertext here. So let's run our program. And we're attempting the different keys, and we have a possible encryption hack here with the key Asimov. Let's have a look at the message here. So we can see this is actual proper English. So let's press D to have a look at the entire message. And if we look at that, we can see this is proper English. So here we can see our key Asimov was indeed the correct key. And even though that's not a regular English word that would be listed in a dictionary, we were able to actually break that message using frequency analysis as well as the Kaczynski examination. So let's have a look at our practice questions, and the first question is, what is a dictionary attack? A dictionary attack is basically trying out all the different English words in a dictionary to see if any of those words have been used as a key to encrypt the Vigenère cipher, and then of course using that key to decrypt our message. The second question is, what does Kaczynski examination of a ciphertext reveal? So the Kaczynski examination can reveal the length of the key that has been used to encrypt a message using the Vigenère cipher. What two changes happen when converting a list value to a set value with the set function? So the set function removes any duplicates, and also the order of elements is being lost, since values in a set, unlike lists, do not have an order. If the spam variable contains the list with the elements cat, dog, mouse and dog, this list has 4 items in it. How many items does the list return from calling set on that list and then turning that back into a list? And we know that the set function removes any duplicates. Inside of our list here, we can see that the element dog occurs twice. So if we call set on it, the set will only include 3 different items. By calling list on it, we're going to get back a list with only the unique items, so with cat, dog and mouse, so 3 items. And let's open up idle to verify that. So here we have our spam dictionary with those 4 items. And then we call set on it and we call list on that returned value. So here we can indeed see now we only have a list with 3 items, cat, mouse and dog, and the duplicated entry for dog has been removed. And the final question is, what does the following code print? So we have a print statement with hello with the second argument end, which is set to an empty string, and then after that print just with the argument world. And the print function by default, when no second argument is passed in, will basically add a new line. So if we were to print out hello without the second argument here, hello would be printed and a new line would be added. But if we actually change that end keyword here to a different value, that will be used instead. So in this case here, we have an empty string. So therefore the second word will be added not in a new line, but right after hello. And to verify that, let's open up idle and let's create a new file. We can save the file under any name, for example, hello-test.py. And then we're going to include the print statement with the end keyword with an empty string and then world as a second print statement. Now after that, let's run our program. And here we can indeed see that a single line is printed out, hello and world are directly printed right after each other, and that's because hello here doesn't have a new line after it, but instead we use the end keyword to remove that new line, and therefore the second print statement world is printed on the very same line. We saw how we can break the Vigenère cipher, but there's a trick that can be used to make it mathematically impossible to break the Vigenère cipher. We're going to cover that in the next video. Feel free to subscribe to the channel to not miss any videos, and see you guys in the next video.